Thank you very much for subscribing to my YouTube channel. If you haven't subscribed, then I would encourage you to ask you to subscribe and also share for others to learn from this educative channel. All right, we're going to continue with the properties of solids, liquids, and gases with respect to their arrangement, their movement, and then their closeness or their separation. Because in your IGCSE chemistry syllabus, you will be examined on the properties of these states of matter with respect to their arrangement of particles, the movement of the particles, and also the closeness of the particles. So please take note of that. Kindly take note of that. Okay, so the arrangement, the movement, and also the closeness. Now, before we delve deeper into these properties, let's look at the diagrams closely. Let's look at the diagrams closely. Now, if you look at the solids, you know a piece of ice um, has an ordered arrangement. Okay, when I say ordered arrangement, the molecules in the ice are closely packed, they are tight. All right, good. So if you look at the diagram for the solid, you see that we have this ordered arrangement. All right, where the particles are orderly arranged. We can describe that as lattice. So when you see lattice, lattice simply means it's a three-dimensional structure, okay, or a 3D structure that is formed as a result of the ordered or the regular arrangement of atoms, all right, or molecules or ions in the case of solids that are closely packed, okay, closely packed. So that is it. Now, if you look at gases, I'll come back to the liquids. If you look at the gases, you could see that um, the gases are far. They are not close. Okay, they are not close, and they don't have an ordered arrangement. So we look at it. Look at that. Okay, and then if you look at the liquids are somehow close, but they are not orderly arranged, okay, as that of the solids. Good. Now, the arrangement. So let's come to the arrangement. Now, the arrangement of the particles, when you are describing that of the solids, we say that solids they have a regular arrangement, or you can simply say they have a regular pattern, or they have an ordered pattern, or you can say they have a lattice. Good. If we come to the liquids also um, are randomly arranged. The liquids are randomly arranged. When we say randomly arranged, it means that they have an irregular pattern. They don't have a regular pattern like that of the solids. So they have irregular pattern or they are randomly arranged. Okay, good. And then also when you come to the gases also don't have a regular arrangement. Yeah, yeah. In fact, the arrangement is highly random. They are randomly arranged. Okay. Now, I will talk about what is responsible for um, the nature of this arrangement later on, later on in the next slide. Now, when we come to their movement, their mobility, or you can say fluidity or the ability to flow, for solids, we say that solids don't move, but they vibrate along a fixed point. Okay, so if you leave a piece of ice cube on table, um, it will stay until it melts. It will stay on the table until it begins to melt, and then later you see it flowing. All right, so for solids do not move, but they vibrate along a fixed point or a fixed position. When we come to liquids are they move around. They move around, and they move around by sliding over each other. So liquids flow or they move around each other by sliding past each other. Okay. When we come to the gases, gases actually move in all directions. We see they move randomly. They have a non-directional motion. They don't move in a specific direction, but they can move in all directions. Right? They can move in all directions. So you can have this molecule moving here. You can have this molecule also moving here. Okay, so it's non-directional. It's non-directional. Their motion is non-directional. They don't have a uniform motion. So they move randomly. And then also we come to the third aspect. The third aspect, that is the closeness of the particles, or in other words, we can say the particle separation. Particle separation. Particle separation means how are the particles separated? How separated are they? The particle separation. How separated are these particles? How separated are they? If we look at solids, solids are close. Solids are very close. And so if you are describing the separation of particles, you say that they are very close. You can also say they are touching. They are touching. So they touch each other. Okay, they touch each other. When we come to the liquids, liquids are also close. Liquids are also close. So if you see this container containing liquid, the liquids are close together. The molecules in the liquids are close. They are close. If you look at gases, the molecules in the gaseous state are not close. So even right from the diagram, you see that they are far apart. They are far apart. They don't touch each other. They don't touch each other. Good. So that is it for that. And next time when we look at some questions, we'll discuss some questions on what we have done so far. I'll bring some examples, and then we'll look at how to answer or how to go about them. The next one is we are looking at these states of matter in terms of the kinetic energy of these particles, the kinetic energy of the particles in these three states of matter. If you take gases, gases have the most kinetic energy. That is why um, the particles spread apart and their motion is random and frequent. Let's go back. Let's go back. Now, look at the diagram, look at the structure closely. Look at the particles in the gaseous state. Now, they are far apart. In other words, these particles have more kinetic energy than the liquids, and even worse with the solids. Okay, so please kindly take note of that. In terms of their kinetic energy, gases have the most kinetic energy, followed by liquids, and then solids have um, the least energy. That is why they don't move, but they just vibrate. Just vibrate. Now, there is a relationship or a link between the kinetic energy of particles and then the attractive forces holding these particles. What do I mean by attractive forces holding these particles? Now, if you look at the particles, for example, if you take water molecule, okay, water, if you take water, water consists of water molecules. Now, so this circle here represents a water molecule. This circle also represents a water molecule. Now, there is an attraction, a force that holds these molecules together. There is a force that holds these molecules together. There's a force that holds these molecules together. And in the solid state too as well. Now, if you look at them critically, you realize that in the solid state, the forces of attraction holding these particles together are very strong. They are very strong. That is why the particles are always closer. They are forced together. The attractive forces are very strong. Now, if we look at it in the liquid state, they are moderately strong. Okay, they are moderately strong, but not as compared to the solids. Moderately strong. They are moderately strong. In gases, we say that there are no attractive forces between the particles in the gaseous state. That is for the ideal gas. But even in the real gas, there are attractive forces, but they are very weak. The attractive forces are very weak. And so we can simply say that there are no attractive forces. That is how come if you look at the arrangement, you could see that they are far apart because the force that needs to bring them closer together is very weak or negligible. And so at every point in time, the gaseous molecules are far from each other. If you look at the solids, they are closer, they are tightly packed because the attractive forces there are really, really strong. Now, there is a link between attractive forces and the kinetic energy. If the attractive forces are greater or are stronger than the kinetic energy, the molecules in that state of matter will be close together. I repeat it again. If the attractive forces, the forces holding the particles, are stronger or are greater than the kinetic energy of the particles, the the particles would always be close together. That is, they will not have enough energy to move away from the attractive forces. But if the kinetic energy of these molecules are greater or are stronger than the attractive forces or the forces holding these particles together, what it means is that the molecules would be far from each other. They will move away from each other. They will not be as close as we see in the solid state. As we see in the solid state. Now, this leads us to an important aspect of this chapter, what we describe as the state of matter. The state of matter. The change in the state of matter. The change in the state of matter. Now, when we say change of state, what it means is that you can have a liquid, matter in its liquid form, turning into a solid. And then also, vice versa. You can have matter in a solid form turning into what? Turning into liquid. For example, if you have a liquid, water, and then you put the water in a refrigerator, after some time, you realize that the water turns into ice, it becomes solid. Why? There has been a change of the state of matter from liquid to solid. If you subsequently put the ice down in room temperature, after some time, the ice turns into liquid. There has been a change in the state of matter from solid to liquid again. When you also heat a liquid, the liquid can turn into a gas. When you cool the gas can turn into a liquid. So that is what we describe as change of the state of matter. We are going to look at it into details. Now let's pick the first one. You have a solid. Look at it. Look at the direction of the arrow. The solid moving to the side. It first turns into a liquid, and after some time turns into a gas. Now, when you supply heat energy to a solid molecule or to a solid, the molecules will gain energy. Is that okay? They will gain energy. And then because of the gain in energy, it's going to lead to a change in state. I will look at this into details in our subsequent um, videos, where we'll look at how the change in temperature affects the change in the state of matter. So kindly take note of that. Now, so from solid to liquid, we say melting is taking place. That is the name of the physical process. The name of the physical process is melting. Right? And then when it turns into a liquid and you further on increase the temperature or the heat, it turns into a gas. We say boiling or evaporation has taken place. I will talk about the difference later between boiling and evaporation. Now, if you move backwards, that is when you remove the heat energy or you decrease the temperature, what happens is that the gas would gradually turn into a liquid. And the name of the physical process is condensation. Condensation. When you keep on decreasing the temperature, it gets to a point where the liquid turns into solid, and that is called freezing. The name of the physical process is called freezing. Now, you can have some substances changing directly from solid without going through the liquid state into the gaseous state. These solids are volatile compounds. They are volatile compounds. When we say volatile compounds, it means that they can evaporate easily. They have very weak intermolecular forces. And so the little energy they can easily convert into the gaseous state. Right, good. So we say that, for example, solid iodine, solid carbon dioxide can easily turn from solid into a gas. All right, without going through the liquid state. So these are the physical processes. We'll take them one after the other. So one, melting. Melting is a name of the process for the transition between solid into liquid. So it is when the solid changes into a liquid. Now, this will require heat energy. This will require heat energy, right? It will require heat energy. You need to increase the heat energy for or apply heat for the process to take place. And it occurs at a specific temperature. So that is what we call the melting point. The melting point. So when we say melting point, is a specific temperature at which a solid turns into liquid, and it's unique to each pure solid. Unique to each pure solid means that every pure solid has its own unique melting point. For example, water melts at 0 degrees Celsius. The melting point of diamond is over 3,000 degrees Celsius. I think 3,550 degrees Celsius. So these are pure solids and they have their unique melting point. They have their unique or specific melting point. And then when we come to boiling, boiling is from liquid, when liquid changes into a gas. When liquid changes into a gas, and it also occurs at a specific temperature known as the boiling point. Known as the boiling point. Now, there is a difference between evaporation and boiling. There is a difference between evaporation and boiling. Now, during evaporation, you have the conversion of liquid into gas. Liquid into gas. In fact, boiling and evaporation have one thing in common. You have liquid turning into gas in each of them, in each cases, for the evaporation and boiling. But the difference here is that now, boiling, evaporation only occurs at the surface of the liquids, where the liquid have enough energy to turn into a gas. Now, when you heat a liquid, some of the liquid gain kinetic energy. All right, they gain kinetic energy and they escape. They move to the surface, and then on the surface they escape into the gaseous state. Right. So evaporation is a surface phenomenon. Right, it's a surface phenomenon. It occurs on the surface. So let's take note of that. Now, when it comes to boiling, boiling does not occur only at the surface, it occurs within and on the surface. Within and on the surface. What do I mean? Now, at boiling, the molecules in the medium, if you are using water, have enough energy. They have maximum energy, enough energy to convert into a gas. So this time, it is not just few of them, but the whole medium, they have enough energy to convert into the gaseous state. And so that is boiling. Right. Now, one other difference too is that boiling occurs at a specific temperature or at a point. So we say water boils at 100 degrees Celsius. Right? So exactly 100 degrees Celsius, boiling takes place. But for evaporation, it occurs within a range of temperatures. And so evaporation can occur, let's say, from 50 to 90 degrees Celsius. You can have some liquid turning into a gas. That we describe that as evaporation. So evaporation occurs over a range of temperatures, not at any range of temperature, because it cannot occur at 0 degrees Celsius. I mean, evaporation of water specifically. So yeah, so the first difference or the differences are: one, evaporation occurs on the surface, it's a surface phenomenon. Boiling is a bulk phenomenon. It occurs both within and on the surface. Two, boiling occurs at a specific temperature, evaporation occurs at a range of temperature. Third one, um, boiling in terms of the time, okay, or the reaction, the rate of reaction, boiling occurs very fast, but evaporation is slow. So it takes place slowly. But boiling occurs very fast. So that is in terms of the rates of reaction. Right? Good. And then freezing as well is when a liquid changes into a solid. The same way applies, it occurs at this, I mean, at a specific point, and is the opposite to of it occurs at exactly the same temperature as that of melting. Okay, for example, water freezes and melts at exactly 0 degrees Celsius. Now, what do we mean here? For example, look at this. Look at this number line. So this zero is like a reference. From here, you move to the positive side, and from here, you move to negative. Right? So water melts at 0 degrees Celsius. So from zero upwards here, okay, melting is taking place. Now, from zero moving towards the side, negative temperature, obviously, you have freezing taking place. Okay, so the zero is like a boundary. Is that okay? All right. And then we come to condensation. Condensation, basically, you're looking at change of state from liquid, I mean, from gas into a liquid. When a liquid comes into contact with a cold region or a cold surface or lower temperature, the gas cools down, the particles lose energy, and they bump into each other. That is, they get closer. They don't have enough energy to escape. And so they are easily turned into a liquid. And that is called condensation. Condensation. And then, as I explained, sublimation is the direct change from solids into, into gas. Now, the change of state is a physical process. It's a physical process, or it's a physical change. A physical change because during this change, new substances are not formed. New substances are not formed. Any change that results in the formation of new substances is a chemical change. So water turns into an ice, it's still water, H2O, just that the state changes. So it's a physical change, right? Because new substances are not formed. New substances are not formed. And then also the change is reversible. You can move from solid to liquid, liquid to solid, gas to liquid, liquid to gas. And then also the substances, after a change of state, retains its chemical properties. That's very, very important. They retain their chemical properties. You know, um, physical chemical changes can also lead to a change of state of matter. Physical chemical changes can lead to a change of state of matter. But if it's a physical change, then despite the change of state of the matter, the chemical properties or the identity or composition of the original substance still remains the same. Thank you very much for your time. Next time, we'll look at the kinetic theory of matter and how the kinetic theory of matter um, affects, or I mean, the change of state of matter. Okay, or we're going to look at the changes in the state of matter in terms of the kinetic theory. You don't want to miss this class. Thank you for watching. Share the link, subscribe to the YouTube channel.